Good evening, everybody. This is Obi-Wan Pez4 and Simplex Pachinko. We are doing some math tonight. So, it appears that the new whiteboard has dropped. Apparently. So we'll also be getting a bit used to that. See how things go. Alright. That's far too small. Experimentation is always the best, especially when you're right in the middle trying to start the stream. Alright. Well, first impressions, it looks cartoony. I have actually used some of this before, so it's not awful. But I'm also hesitant because I'm a little worried that I'm going to click something and I'm going to dox myself again. Always happens. Alright. Well, the other thing I do like is that I'm now kind of overlapping with this dock here. The panel. We can close the panel, but also when we hit create, it'll open it up for whatever we need. Okay. So today is 2022, 406, and we're doing series Cock2. That, of course, is subject to change. I have no idea what anybody else is interested in doing, but we've got some stuff to explain tonight so that we can, so that I can do this tomorrow when I have stuff in class. So, man, I missed this whole section. I don't know what happened to my head. So there was a whole bunch of stuff on first order linear differential equations and its applications and things like that, using integration factors and doing all sorts of stuff. And I apparently just missed it or something. It's weird. The children might be revolting. We'll see if that becomes my problem. Okay. So I do want to start on series and sequences introduction. Alright, there we go. So, so if we're going to do stuff with sequences, what we're talking about is a list of numbers. And in any list of numbers, we're going to have those numbers themselves plus commas, which are going to allow us to write all of them out. And, oh dear. Huh. Wall 6996. Exploring an odd number idea. I mean, I'm up for hearing about just about anything, so. So, welcome in. My name is Obi-Wan Pez. This is N Simplex Pachinko. Alright, go ahead and pop that on in. Here we go. Multi-base numbers, oh goodness. So each digit is a different base. Interesting. Okay. Do you have a particular interest in, like, vested interest in that in particular, or are we using Do you have an application in mind? So what you're saying is if we list the numbers like A, B, C, D, E, F, this would be F times, not 10. To the first plus E times 3 to the first or second? Okay. No, I know it was a dangerous thing for me to ask. Do you have any particular application in mind? Because theoretical mathematicians can start throwing things across the room if that's the case. Mm-hmm. That's not it at all. Okay, interesting. Alright, how does one represent numbers in that particular system? I mean, you've got all the ones up there, but okay. Multi-base representation compared to its decimal equivalent. Hey, two Gerbs. Solve a to the b equals c for a without using roots, and instead use logarithms and exponents. Yeah, that can be done. Alright, so for right now, Wall6996 came up with an interesting representation for numbers. So here we said, so here they said, each individual digit is going to have a different base attached to it. So the first digit here is base 2, the second digit is base 3, the third digit is base 4, etc. I mean, yes, there is a different way to write the nth root. Oh, interesting. Somebody else just started their stream. She's usually not until much later. Alright, so here we got F is going to be base 2, E is going to be base 3, D is going to be base 4, C is going to be base 5, B is going to be base 6, and A is going to be base 7. And you're saying that the nth digit starts at n factorial. So I think that that's kind of an interesting result just by itself. Oh dear. Yes, the children are revolting. Possibilities are 0, 1. Possibilities here are 0, 1, 2. Possibilities here are 0, 1, 3. Oops, 0, 1, 2, 3. Undo's way over there. Through 6 on A, etc. Okay, so what other? Yeah, that's really cool. What other things do we need before we can actually use this? So it's been so long since I've done any of the like abstract algebra stuff, but like, do these numbers need to have any particular group properties or anything like that in order to, you know, more formally make this work? I guess it would need to be a group if we just want to say, like, what properties does it have? Does it have the properties of a group? And then does it have the properties of some sort of, like, yeah, is it abelian? Is it not? And I don't remember how to do any of that. But field. That might also be. addition, subtraction, multiplication, and division to find and behave as corresponding operations on rational real numbers. It feels like they do. It's going to be a little bit strange just because of how the numbers are set up, but I think that it seems like they should, you know, behave the same way at the very least. Well, hang on. Who's it? What's the International Database of Sequences? Online Encyclopedia of Integer Sequences, OEIS. There we go. So if I search 1 1 0 1 1 2 0 2 1 right, 1 0 0 1 0 1 1 1 0 1 1 1 1 2 0 1 2 1 2 2 0 0. Right, if I search this, I should be able to come up with something then. Yep, there we go. It is called a factorial base. And I will link that directly in the chat. So, integers written in factorial base. oeis.org/A007623. Yeah, it wouldn't necessarily change anything. You're right on that one. Authors N.J.A. Sloan, Robert G. Wilson, and Mira Bernstein. (2012) looks like. That doesn't necessarily mean that that was the first time that this showed up, just that first time that it was put into this system. Okay, so factorial base actually starts with, this would be a times 7 factorial plus b times 6 factorial. Let's see, 6, 5, 4, 3, 2, yeah. Plus c times 5 factorial plus d times 4 factorial e times 3 factorial f times 2 factorial. Or is that the other way? Yeah, it's all shifted one down from there. Alright. F is 1 factorial. E is 2 factorial. D is 3, C is 4, B is 5, and A is 6. In this particular number. Alrighty. Good times. if there's anything in particular that's really cool, you know, please let me know. Bring that one back. Because I like to figure out, you know, hear some more about it. Primordial base. Is that the primordial LB? A267856. Oh. A049345. Thanks. Really? No, N written in primordial base. I don't know. I hit search on primordial base and it came up with something completely random and not this. It's just... 1263210. Yeah, okay. Yeah, okay. That's fair. Yeah, I didn't even notice. I've been not incredibly paying that much attention to the alternate external links, or, well, internal links to the other ones. Anyway. Okay. So, two curbs. I know that I can answer your question with relative confidence. So if we have something that looks like this, a raised to the b equals c, you can definitely just take a log of both sides. And it doesn't actually matter which one you do. I tell my students all the time, the only reason that I use natural log is because I do it in cursive. And it's just faster. Because if I have to write log like that, it takes twice as long. So I just explicitly use natural log, and again, it doesn't matter because you can just use the change of base formula to get whatever base you feel like. Alright, so here we know that this is going to come down. So this is going to be b natural log of a is equal to natural log c. Yeah, doesn't really matter if that's there or not. Alright, then b is going to come over here. Oh, you're going to hate this. Oh no. I just saw what happened. I just saw what's going to happen. Alright, so b is going to come over. We get the natural log of a equals 1 over b natural log c. So here's the issue. You said you didn't want to use roots at all. But either your 1 over b is going to have to come up inside of here to c. And then you get a equals c to the 1 over b. I mean, that's eventually, right? After like 2 or 3 steps, you end up here. Or you say, here we're going to raise e to these powers. And again, well, okay, that's really getting us back here anyway. But e raised to the stuff ends up with a equals e to the 1 over b times natural log of c. either way, this is really using a Beath root. So one way or the other, it's going to happen. Yep. Yeah, I was kind of curious there for a second whether it was going to... Yeah, I got you. I was kind of curious whether or not it was going to have a different representation using, you know, slightly different things, but no, it's all the same. Oh well. So that is going to be that. Okay. No, not today. All right. Anybody have anything else? Random other stuff you want to talk about? Oh, nice. Well, congratulations on making some headway. English is my first language, I promise. Oh, man. Could just be that I'm really just that tired. I started just rambling one of my classes today. I was like, no. Let's just stop talking. Coin balance puzzles. Possibly. At least I may have heard of something like it. Is this one of those where you have a stack of coins, you put them on the edge of the table, and then try to see like how far out you can make the stack move? There's a good... There's a good, Oh, yes. Yep. Yeah, there was also a... Alright, go for it. It's probably going to go horribly wrong for me, but alright. That was not it. Alright, if we have... There we go. Oh dear. 22 stone idols and a strange three-way balance. Oh man. Three-way balance, okay. Uses draining water to operate at one end of the room with locked door with 2 spots for stone idols, as well as some inscriptions. Deciphering the inscriptions, it appears that placing the alpha idol on the left spot and the omega idol on the right spot will open the door. But if any idol besides the correct idol is placed on a spot, a deadly trap will be sprung. Yeah, okay. Inscriptions also state that idols, while looking different, all weigh the same, except the alpha idol is slightly heavier, while the omega idol is slightly lighter. And they are such that the two together can masquerade as any 2 other idols. Okay, so their average weight is the same as all the others' weights. So, probably unhelpful. Can only operate the balance 3 times. So, like, the way that I'm reading it, checking the idols on the balance at all is a risky behavior. So, like, you're gonna die if you put them on and they're wrong in any way, shape, or form. But I mean, clearly that's not. I'm assuming something is not correct in there. Anyway, this picture was taken a few years ago. I stacked up these Jenga blocks and... Oh, okay. Gotcha. Stacked up these Jenga blocks and said, okay, if I push them as far out as they can go, that way. If I push them out as far as they can go and then move up and push it over a little bit more and push it up, move over a little more and go up, move over a little bit more, and eventually this ended up forming, and I ended up taking a logarithmic regression of this thing, and r squared here is 0.9976, so that's a pretty good logarithmic approximation. It of course also drops off really fast after that, so like, okay, whatever. Wait, hang on. Oh, no, that's fine. Yeah, the black one was like quartic maybe. So it also was a decent regression, but had a slightly smaller value, r squared value, and again, extrapolating, it just drops off real fast, so that doesn't really work. But with the exception of the last point here, our logarithmic regression does really well. So like I think you should be able to do up to 27, maybe 26 idols in order to get that measurement with 3. Do them all correct. The only problem would be if you're wrong on the first one and you end up having okay, if you got 22, split them into groups, even groups of 7. Best case scenario in that case, groups of 7, you've got 1 remainder. Best scenario is that the remainder is one of your idols, either the heavier or lighter one. And then one of your groups elsewhere on the thing is also going to be the opposite. Again, either slightly heavier or slightly lighter. Then you can immediately eliminate the other 2 groups. And then you're going to take those 7 and split them up into groups of 2. Yeah. Start easy, go hard. So split them up into groups of 2. And then you're going to have 2, 4, 6 with 1 remaining. Measure those again. Again, if it's not balanced, then, or if it is perfectly balanced in that case, then your remainder is the one that is going to be the other. Otherwise, right, you'll know which group is heavier or lighter, and then you get your third one will measure the one group. Alright, so worst case scenario is that the 2 of them are on the same pad initially. And so they average out to be the same as 2 of any other idol. And again, there are 7 on each. So if there's 7 on each, and they all appear to be fully balanced. Yeah, I think it might be screw there. Or if there is, there's an elegant solution that I'm at least not seeing immediately. So maybe I can figure it out eventually, but one other option might be that seems dangerous. Alright, so if you try to do something like this, this would allow you to measure 3 and keep 1 off, which again, you could immediately figure out which was which. If you did that one. Then you're screwed if this is perfectly balanced and these are all the same, because like these two are going to be alpha and omega, so they're yeah, how would you do this? It's like this is the worst case scenario where you're going to have 2 of them in the same group somewhere. You don't know which ones they are, but they weigh together the same as any other pair. Yeah, I'm gonna need some time on that one. Really? Oh, guys, come on. I'll just move. No, that's not that. Cool. Alright, I don't know how this works. Cool, cool. Also true. Oh, come on. There we go. Yeah, I'll poke around with that one a while and see if I can do anything with it, and then might have to eventually. Right, so most of my students at this point have seen sequences in pre-calc. So I probably don't have to do a whole lot in terms of crap. We're going to need a list of numbers, and again, it's written. A sub n is going to be equal to, and then we can write a set of numbers like this, and say it's like or no, it ends with that's not it. Yeah, that's not. Goodness. All right. This is why I'm doing this, so I can screw up tonight. So it can be that like a sub n is equal to, and then you list a series of numbers. If you're using that particular notation, you don't actually use a sub n, right? Yeah. Okay. It's not So if you have something like 1/2, -1/2, a fourth, -1/8, 1/16, etc., then this is going to work out. We want to find an explicit formula. I'm just going to have defined as function of the index variable n alone. So in the one above, we're starting with the number 1. So n is going to be equal to 1 times, and then we're multiplying by -1/2 every time. So -1/2 raised to the n minus 1. Although this could also be this is -1/2 raised to the n. Then on the first one, we want this to be a -2 times -1/2, since n value of 1 would make this -1/2, multiply the -2, and you get +1. So either of these are perfectly fine to use. And then we also want to think about implicit form. This can be defined as a function of the index and or any previous terms. Of the sequence. So in the one we've got up above, we're going to say that any a sub n is going to be equal to a sub n minus 1, the previous term, multiplied by negative 1/2. Another famous one for implicit form. It's going to be f of n is equal to f sub n is equal to f sub n minus 1 plus f sub n minus 2. So any value in the sequence is going to be given by the sum of the previous two. Right, so it's going to be the Fibonacci sequence. And this has no explicit form. This is an implicit form. Okay, so something that has an explicit form but doesn't really have an implicit form. I'm not even necessarily sure this will 100% work, but I do know something that's really gross, like a sub n is equal to n factorial times negative 1 to the n times the cosine of, well, sure, why not, cosine of n. So since this is discrete, the cosine of n is going to just be kind of nasty numbers, and it's going to start drifting because it's not the cosine of pi n or something like that, it's just the cosine of n. Alright, so with n being 1, a sub n is going to be 1 factorial times a negative 1 times the cosine of 1. So this is all just a big negative cosine of 1. With 2, we've got 2 factorial is going to be 2. Squared is going to keep it positive. So it's going to be 2 cosine of 2. 3 factorial is going to be 6. This is going to cause it to be a negative this time around. So negative 6 cosine 3. And 4 factorial is going to be 24. It's positive this time.